Okay, so in chapter 4, we were doing stoichiometry, lots and lots of calculations, very little concept though. In the first unit, there was probably a lot of concepts and maybe a little bit of calculations. This one is fairly evenly matched between concept, writing equations, understanding the chemistry, and the calculations involved. So just keep that in mind, and when you're studying the concept side, recognize you probably need to do a little bit more reading and like rephrasing for yourself what a particular idea means. Okay, so for example, the definitions of solutions. So chapter 5 is all about solutions, which is a liquid with something in it. So usually we're talking about an aqueous solution, aqueous meaning water, where water is the main component, and then we dissolve something else into it. So water in that case would be called the solvent. Whatever is the greatest amount in this solution, this liquid, that's called the solvent. And then the smaller amount, the thing we add in, that's the solute. So you add sugar into your tea. Let's pretend the tea is mostly water. The water is the solvent, the sugar is the solute. Or you add a Kool-Aid packet into water. The water's the solvent, the Kool-Aid, the sugar, the flavors, the colors. Those are the solute. And we can talk generally about concentration. So concentration tells you how much stuff there is in that solution. So like if I had a gallon of water and I added 1 packet of Kool-Aid to one, and then I added 2 packets of Kool-Aid to the other, the one that I add 2 packets to would be considered more concentrated, and the one with 1 packet would be considered more dilute. So in this picture, you see if there's less solute particles in that same amount of liquid, we would call this dilute or less concentrated. And the more particles there are in that same volume, we would say it's more concentrated. Those are very vague terms, right? Those are conceptual terms, qualitative terms, not quantitative. The time you've probably seen quantitative measures of concentration is some kind of chemical that you buy, like a household cleaner or medication, and those are usually given in percentages. So like the example I thought of earlier was hydrogen peroxide. So like when you buy hydrogen peroxide, in the brown bottle for like a disinfectant for wounds and stuff, that's 3%. So what it means is that every 100 milliliters, 3 milliliters of that is actually hydrogen peroxide. The rest of it's just water, because they don't want people putting like very concentrated hydrogen peroxide and killing off some of their skin in the process of trying to disinfect it. Okay. If you go to I think people use 10% peroxide if they're trying to dye their hair. Wouldn't recommend it. But 10% now means you've got 10 milliliters in 100 milliliters of that solution. And then if you go to like a chemical supply place, you can buy hydrogen peroxide in 30%, and that's what we would use in a laboratory setting. So that would be 30 milliliters in 100 milliliters of solution. So those are quantitative ways to measure how much stuff there is in a given liquid. Keep in mind, in chapter 4, we were measuring everything out in grams, right? We always converted grams to moles in order to do a chemical reaction. Now we're talking about having a liquid so that we can convert that liquid into moles. So that's really all we're doing, is having like an additional way to get us to moles and be able to perform calculations, chemistry, balanced equations. So yes, we're going to keep doing stoichiometry. It's just that, I'm looking for a blank page. I'll do it here. It's just that before, in chapter 4, we were going from grams to moles, and then we would do a mole to mole conversion, right? So maybe it's moles of A, and then we convert to moles of B. Now we're going to do a volume, so either liters or milliliters, and we're going to measure how much of that liquid that has the Kool-Aid in it or whatever, how much of that liquid, the peroxide, do we need to pour out to get a certain number of moles of that compound? Okay, so when we did grams to moles, we used molar mass as our conversion factor, right? The masses from the periodic table. So we need to know what we can use here to convert from a volume to get us into moles, because that's what we always care about when we're doing a balanced chemical equation. We care about moles. So the unit or the conversion factor that we use to do this is called molarity. And the units of it are moles per liter. So what that means is if I have a given solution, let's use the peroxide example, if I have a liter of solution, the molarity would tell me how many moles of peroxide I have in that liter of solution. So unlike percentages, this connects it much more directly to the number of moles. In Chem 2, we'll do lots of other concentration units other than molarity, but in here, we're just going to stick to this one, okay? So all today, we're going to talk about how to determine molarity, because it's not as easy as just looking at the periodic table. We're going to determine molarity. We're going to use it as a conversion factor to tell us moles, as well as some other things like reversing it. If we already have moles. And then we're going to do how we prepare a solution of a particular molarity. And yeah, that's about it. Okay, so I'm going to scroll back up to this problem. So this is where we formally get that definition of molarity. So molarity is the amount of solute measured in moles over the volume of solution in liters. And if you haven't noticed already, it's a unit over another unit. Just like grams per mole was a unit over another unit, or density, grams per milliliter, was a unit over another unit. So you can be pretty darn sure that this is going to be used as a conversion factor. The difference is we can't know this value just by looking it up in some table, because it really depends on how the solution was made. Was it, enough peroxide to make a 10% solution? So I'm totally, let's just pretend that it's 0.1. It's not. But let's say, is it 0.1 moles in a liter, or is it 0.3 moles, or is it 10 moles, right? It depends on how much peroxide you added. And there's lots of different concentrations available that you could buy or make yourself. Okay, so we're going to start with this example where we dissolve 3.88 grams of sodium hydroxide. So sodium hydroxide is a base. Drano is like a very common example of sodium hydroxide. It can come in a solid. It also can come in a liquid that's very concentrated. But we're saying we're going to measure it out as a solid, 3.88 grams, and we're going to put it in a container and make the whole volume 0.150 liters. Okay? So I want to know, what is the concentration, like how much moles per liter do I have? So I want you guys to take a shot at this. Now, usually we use a conversion factor to find out something. When we're creating a conversion factor, we need to solve the top, solve the bottom, and then divide one by the other. So I want you to use this 3.88 to find the moles, and then you're given the liters, and then you're going to divide one by the other. Okay, so take maybe 2 minutes and determine each of those. And then find the overall molarity of this solution.
Mm-hmm.
Okay, so in this problem, you're gonna have moles over liters because you're trying to determine the molarity. You're not using the molarity in a problem yet, you're trying to determine it. So I need to have the moles, and then I'm gonna divide it by the liters. So all I have to do here is convert to moles first, then divide moles by liters. And this tells me now how many moles are in 1 liter. By doing that division, you're kind of equating things so that you can compare them easily to other molarities. Sorry, I was gonna move this over. And there we go. And when you do this, the unit you use is molarity. We abbreviate it with a big M. But don't forget that big M means moles per liter. Lots of M's in chemistry. So moles is MOL. Molarity is a big M. There's a little m that we'll learn in second semester, so don't use that yet. And molecule, you have to spell the whole thing out. Trying to remember if we have, I think molar mass, sometimes people abbreviate that as big M, or big M, big W for molar weight. But I don't ever use that as an abbreviation. I just write grams per mole. Okay? So what does this tell us? This tells us that in every 1 liter, I have 0.647 moles of NaOH. So I've created this conversion factor now that will allow me to figure out different problems using this molarity. Okay, it also gives me a very quantitative way of describing how concentrated or how dilute it is. If this is 0.647 and I compare that to a solution that's like 2 molar, that's much more concentrated, right? Or if I have something that's like 0.01 molar, that's quite dilute. So all the properties of the base NaOH are going to be much more significant the more, so NaOH is corrosive. If you pour it in as Drano, it's gonna eat up like all the nasty garbage that's in your sink, hair and whatever. And it does that because NaOH is corrosive. So if you have a very concentrated solution like a 2 molar or even a 5 molar solution, that's gonna be better at being corrosive than say a 0.01 molar because it's more diluted. There's less NaOH in a given amount. Okay? All right, so now we're gonna do a problem. We'll get to this in a second. Well, no, I'm gonna show this to you now. So this is the first time that I've showed you guys these simulations. This website has lots of different simulations for chemistry concepts. So you can always go and look for one. I'll highlight the ones in the notes, like put the links there for you to use that I think are particularly useful. I didn't love the just straight concentration one, but the molarity one is useful. So I'm going to show that to you. Mostly the link is there so that you guys can use it later on. Okay? There's also an app for this. All right, so I'm going to switch this to, what were we doing? NaOH, that one's not on there. Let's do, I was trying to look at something that was relatively simple. I'm just going to do potassium permanganate because it's pretty. So this is like a really deep purple color in real life. All right, so I'm going to decrease the amount of solute, if you see on the side, meaning like let's pretend that I only added 0.1 moles of this in 1 liter of solution. Okay, if I did that, the molarity would be, oh, that's because I didn't get it quite at 0.1. So let me try to wiggle it up there to exactly 0.1. It's close. I can't seem to get it. So let's pretend it's 0.103. It's the closest I can get it. So if I have that number of moles in a liter, then the molarity is 0.103 moles per liter. Okay? But if I have that amount in less volume, like half that volume, then it's going to be twice as concentrated. I didn't change the amount. I just changed how much liquid there was. Pretend like I have this sitting out on the counter for like a week. okay? And some of the liquid, the water, evaporates, but the amount of potassium permanganate doesn't change. So it starts to evaporate. Look at what's happening to the concentration. It actually gets more and more concentrated, not because I'm adding more potassium permanganate, but because my amount of solvent is changing. So it's very contingent on both of those things, the number of moles and the number of liters. If you increase the volume, you're going to make it more dilute. If you increase the amount of the solid, you're going to make it more concentrated, but you can change it both ways. So you can play around with that as you're working if that's useful for you. Okay, so let's talk about, we calculated the molarity of this solution. We said we have 3.88 grams in a 0.15 molar, a 0.15 liter solution. Okay, so it almost sounds like we're making that solution, like we're putting 3.88 grams and then we're adding so that there's 0.150 liters. So we do this in a laboratory setting lots of times. We make solutions and there's a pretty precise way of doing this. So we use what's called a volumetric flask, which is a measuring device that's for one particular amount of liquid. So you can get a volumetric flask that's like 10 milliliters or 25 milliliters or 50 milliliters or as big as 1 or 2 liters, but you only use it to measure that amount. So you use it to create a particular concentration of a solution. So in this case, they're doing sodium chloride, and this would be how to prepare a 1 liter solution of 1 molar sodium chloride. So initially people might think, oh, you just take a mole of sodium chloride, which is, the mass is there, 58.44 grams. Okay, so I take 58.44 grams of salt, I put it on my balance to make sure it's the right mass, and then I add a liter of water. No, because the units are moles per liter of solution, not liter of water, right? And the 3.88 grams takes up some volume. So it's not going to be exactly a liter if I do it that way. So the way that we do it is we add the amount of the solute, the sodium chloride. We put a little bit of water in to get it to dissolve. Usually you mix it up at that point. Then you add the rest of the water till you get to that mark that's on this very precise measuring device, the volumetric flask, so that the bottom of the curve is right at that line, and then you mix it again. And once you do that, now you have a very precise measurement of a liter that you know you put 1 mole of sodium chloride in, okay? So when a question asks, like, how do you prepare this solution, you need to first figure out how many grams do I add, and then you would go through this process. If you selected an answer, like let's say it's a multiple choice question, and you selected an answer that said, add 1 liter of water to 58.44 grams of sodium chloride, that's not right, because you want the total volume to be 1 liter. I know that seems like a minute thing, but when you're doing chemistry and you need to know precisely how many moles you have of something, you have to do it this precisely. You have to make sure that the total volume is 1 liter, not that it was like 1 liter of water and then that's solid, okay? Because that solid adds some volume. All right, so we'll do that in a little while. We'll talk through, or we'll do a calculation that involves that. So like, let's pretend that we already have a solution though. You can ignore these ones. Those are just for example. They're not the actual conversion factors we're going to use. I'm just reminding you that if you have a molarity, you can use it as a conversion factor. Why? Because it's a unit over another unit. Okay, so looking at this question, how many milliliters? So I'm looking for milliliters. How many milliliters of a 0.4 molar sodium sulfate solution are needed to supply 0.0750 moles of sodium sulfate? Okay, so people start to be like, I don't know what that question asks. Let's do it the same approach that we've done every single time. We're looking for milliliters, and then we're like, what do we start with? And this throws people because they're like, there's 2 numbers there. There's never 2 numbers. There's always just 1. So what you have to recognize is that the big M, molarity, is a conversion factor, okay? So this is going to be conversion factor. This is going to be used in the calculation. It's not where you start. So you always want to start with the number that has a single unit attached to it, and then save the one that's a unit over another unit to use as a conversion factor. Similar to like density, right? If you're given density in a problem and mass, you start with the mass and then you use the density as a conversion factor. So in this type of problem, we would start with the moles of sodium sulfate, and we would convert from moles. Now, can we go straight from moles to milliliters? No, because molarity, every time you see molarity, I want you to think moles per liter, moles per liter. It's on your exam equation sheet. Like, you guys generally don't use that as much as you probably should. Okay, so molarity is right here. Molarity is moles per liter. You're not going to use this one or this one or that 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 one till semester 2. Okay, so just the top one is pertinent. Yep.
You put .07 under this .07.
Oh, you're always so good at, the 5 is just terrible handwriting. Little more space there. Thank you. Okay, so I can't go straight to milliliters, but very often my measurements will be in milliliters. Why? Because think of everything you've ever done in lab, like those flasks, those cylinders, those are usually in milliliters, because rarely are you measuring an entire liter of something. And if you are, you're probably going to be measuring fractions of it. So we're going to have to first go to liters and then go to milliliters, which we know how to do. It's just a basic metric conversion. But that's going to be my setup for this calculation. We'll put the numbers in a second. But we're going to go from moles to liters and then to milliliters. Why? Because the question asks for milliliters and it starts with moles. How do I know I start here? Because it's a single unit. Why don't I start here? Because that's a unit over another unit. So it's going to be used as a conversion factor. It's very, very similar to when we use molar mass and we use grams per mole. The difference is the molarity is on the periodic table. The molar mass is, I just said it the other way around. The molarity has to come from the problem. The molar mass is on the periodic table. So it has to be given to you. You can't just look it up somewhere. Okay, so putting in the numbers, we're going to use that molarity here. But remember, 0.4 molar means 0.4 moles per 1 liter. So I better make sure that the 0.4 is tied to the moles, and then it's 1 liter. What we're really doing is dividing the moles by the molarity, but we just write it as 1 over that number of moles. Okay, and then because we generally measure things in milliliters, then we're just going to go ahead and convert to milliliters using the metric. So you can write it like this, or you can write it like this, which always baffles me why people would think that's easier, but that's what your textbook tells you, so I always want to remind you that that's okay too. Okay, so punching this in our calculator, I get 18.75. Now, technically, this is 3 sig figs, so I'll say 18.8. Do you have to know that? No, but the answer is going to be written as 18.8 in the list, not 18.75. So as long as you can pick what's closest, that should be fine. Okay, so what did that actually mean? It sounds like what we're doing is we're doing some kind of an experiment where we need 0.075 moles. And we're trying to figure out how do I get that 0.075? Apparently, I'm not allowed to just measure out a mass to get 0.075. I have to start with this solution, this liquid, that contains 0.4 moles for every 1 liter. So this calculation tells me now I'm going to pour out 18.8 milliliters, and in that 18.8 milliliters is going to be 0.0750 moles of sodium sulfate. So that's what the calculation is telling you, what you're actually doing there. Did I do the math wrong, or do you have it?
Getting 187.5.
0.07. Here, let's just plug it in. 0.07, so we can see. Could be me. 0.0750. Oops. Okay, divided by 0.4. And then times 1,000. Now you could have divided, oh, it looks like it was me. 0.07. Okay, now it's gonna drive me nuts. I gotta go look at my history to see why. Oh, because I did times 100. You're right. I missed a 0 on the end. Thank you. Okay. Extra 0 there. 187.5, or rounded to 188. There's our decimal there. And we'll change this to 188. Okay, so just kidding. Not 18.8 mils, 188 mils you're going to pour out. So in the case of sodium sulfate, that's kind of dumb because most of the time you're going to weigh out sodium sulfate. Most ionic compounds are solids, and so it's pretty easy to just like scoop them out of the bottle. But in this example, we're saying it's a solution. Now, some things only come as solutions, like acids. Most acids are not solids. They actually, like the way you make hydrochloric acid is you take water and you bubble hydrogen and you bubble chlorine gas through the water, and it produces a particular concentration of HCl. You can't measure out HCl, okay? So some things we have to do this with because they only come as liquids. All right, why don't you guys take a shot at doing this calculation, and then we'll add one more point to it that incorporates this idea of buying a liquid and how you deal with it if it's not the concentration you want. Now this one says describe how to make. Remember, when we do that, we want to determine the grams that we should add to the volumetric flask, and then we fill it up to 2.5 liters. The aim here is that we're trying to get 1.2 molar solution. Okay, so I'm looking for grams of potassium permanganate. So that's what I put at the end. I can only start with liters because this is a single unit. That's a unit over another unit. I know it looks like it's just a unit, but remember molarity is moles per liter. And then I'm trying to get to grams. So I go from liters and I use the molarity to get to moles. That's not grams yet though. I have to then use the molar mass to get to grams. So this is where like you have to start pulling from the recesses of what are potential conversion factors that I know. I know grams per mole, right? That's what's going to help me get from moles to grams. I know I'm going to use the molarity in there because they gave it to me. It's moles per liter. Where do I use it? Well, I'm starting with liters. So sometimes you just kind of have to like infer from what's given to you in the problem what you can use when, and sometimes you're pulling it from your brain of what potential conversion factors you know or that you've used before. We've never gone directly from liters to grams, right? That's not possible. We've never used that before. So don't try to say, oh, liters on bottom, grams on top. Because when you look at that, you should be like, I don't know grams per liter. That's not a thing we've done. So you're not going to use that. You're going to use the moles and then use the molar mass. Has anybody solved this? What does it come out to be? Okay, I'm going to leave it as actually 480 because this one only has 2 sig figs. Again, you don't have to know how many, but just realize that's what it's going to be reported as in the answers. Oh, sorry, 474 you said, right? Yeah. 470. So how would I do this? I would add 470 grams of potassium permanganate to a 2.5 liter volumetric flask. It's going to be pretty big. I'm going to, anything over a liter, they consider drug paraphernalia. So like obviously in an educational setting, that's okay. But like you shouldn't have a 2.5 liter volumetric flask or it would be considered drug paraphernalia. Which for my 21st birthday, a bunch of my friends bought me a bunch of stuff like that just to be funny. Like, here's this round bottom flask that's over a liter. Haha, what a dorky thing, right? Okay, so 2.5 liters. You add 470 grams, you put some water in it, you dissolve it, you mix it up, and then you fill it up so that it's a total of 2.5 liters. When you do that, you now have a 1.2 molar solution. Okay, so that's how you made that original solution. Then you can use that to determine, how much you're going to use in a particular experiment. Okay, last thing. Lots of times you're not making it from a solid. Like I said, there are certain chemicals that only come as liquids, but they come as a concentrated liquid. So like HCl comes as 12 molar HCl. Sulfuric acid comes as 18 molar sulfuric acid. We would never let you guys use 18 molar sulfuric acid in an experiment because we don't want you to kill yourselves, okay? So we dilute it down to maybe like 0.5 molar or maybe even like 0.1 molar. The question is, how do we dilute that? What does dilution mean to you? If you have Kool-Aid and it tastes too sugary, what do you do to make it taste less sugary? You add more water, right? It's the same thing as if you're diluting a concentrated solution. Now, usually we don't take the whole bottle of sulfuric acid and just add water. We take a small amount of the sulfuric acid. So this one's for, calcium chloride. Let's just pretend it's my example. We take a small amount of sulfuric acid. We use one of these volumetric flasks again, and then we add water and dilute it. So we take a small fraction of it and dilute that. And to calculate this, we use this dilution equation. This is one of the few times where I give you an actual equation rather than you having to set up a calculation. So you're welcome. You're not going to be as happy with me as you think because you guys don't know how to do algebra as well as you think you do. Dimensional analysis is generally better. Okay, so we're going to do a practice with this, and we'll do another one on Wednesday since we're right at the end here. Okay, how many milliliters, so that's going to be a volume, of a 0.08 molar, so that's going to be a molarity, sucrose solution do you need to make 250 milliliters? So we'll call that volume 2. That will be 0.015 molar. So we'll call that molarity 2. So we just plug this into the equation. M1V1 equals M2V2. Or molarity 1, 0.0800 molar. V1 is our unknown. M2, 0.0150 molar. V2, 250. Now this is in milliliters. These volumes, if you do one in milliliters, the other will be in milliliters. You can also do it in liters, and the other will be in liters. So it's kind of nice. You don't have to change it. Now, if your algebra is poor, realize you're going to have to divide both sides by 0.08. Okay, that's how you do that. If you don't know how to do that, you need to go to a math tutor because that is not something that I'm going to teach you. I expect you know that. So this is, watch me do the math wrong and then I'll be like so embarrassed. 46.875 milliliters is V1. Okay, that's how much of the original solution, the 0.08, you're going to use. And then you're going to dilute it to a total volume of 250. That'll give you this 0.015 molar. Okay, we'll start here and do this next one as a warm-up on Wednesday. Yeah. Yeah. Did you do times 4? Oh, yeah, you need to. You do times 4 and then this is manganese and that is lithium. That should be right. Yes. 1 second. Oh, like the dynamic study modules? Yeah, those ones are required. Yeah, if you go back and do them, I will definitely give you 50%. So that's kind of like my default. I'll never go past that. And then just email me once they're done, and then I'll update the grades. Okay, well, I'm good you did. Glad you did now. Yes.
How much do I get for reading if I do this? I didn't realize it was still this much. I thought it was due later than that.
So that was yesterday, right? So it's just a day late, so it's 10% off per day. It'll automatically calculate that for you. So just do it by the end of the day, and it'll be 10% off. But
Is there anything else that we acted on then? And all that I'm not aware of?
so if you're on Pearson, it always has the due dates. So you need to go in and be following those due
Is
dates.
there any way I can have it give me notifications or anything the timing?
So this is kind of that study skills thing. The best thing to do is go into Pearson, look at your due dates, and have a calendar for yourself and write it in there. Because like you need to keep organized on what your due dates are. Do you not use like a calendar or a task management software?
But it's always so cool. It's still big.
Yeah. Okay, I know. That's one of those things though, you gotta be taking care, it's not gonna give you notifications. You gotta take care of keeping track of those deadlines, okay?
Have you graded the test yet?
Yeah, it's in Pearson.
Okay.
Sorry.
It's okay.
I didn't send an email or anything, I just put them in there.